everybody! Welcome back for another amazing video, brought to you by...
Us.
Yes, exactly! I am Beaks, and welcome to another learning video.
Today we are going to be learning about cylinders and cones. These over here are cones, by the way. But before we get into cones, let's learn about cylinders. Let's look at a cylinder. What first comes to mind when you think of cylinder? You might think of prism, like a 3D prism. Like, you know, the one with the two circular bases and a bent rectangular lateral face. That is a cylinder. This is also a cylinder because although it is smaller and thinner and yellow, it is still a cylinder because it has two circular bases, one on the top and one on the bottom, and it has a bent rectangular lateral face. So as long as it has two circular bases, one on the top, one on the bottom, and a bent rectangular lateral face that allows it to roll and stack, then it's a cylinder, all right. Yes, we could prove that the lateral face is a bent rectangle, because if we unfold a cylinder and show its neck, the lateral face, or the body, as I like to call it, is a rectangle shape. And the two circles, which are the two bases, sit on the rectangle. So yeah, that makes sense. So when we fold the rectangle and the two circles together, we should get these shapes. So yeah, these show the bases and this shows the lateral face in the middle over here. Let's look at these kinds of cylinders. These are translucent because it only allows some light to pass through. But it could also be transparent because you can apparently see all of the insides. But it's theoretically translucent. But these are opaque because no light can pass through them. And you can't see the inside. But anyway, enough about that. These are also cylinders because even though they are a lot smaller indeed, and all of them are the same size except for this one, they are still all cylinders because if we look at all of them, two circular bases, check. Two circular bases, check. Two circular bases, check. Two circular bases, check. One bent rectangular lateral face, check, 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 and check. Roll and stack. Roll, stack, check. Roll, stack, check. Roll, stack, check. And roll, stack, check. So, all of them are checks. So we could prove that these are all cylinders because they all have two circular bases, they all have a bent rectangular lateral face, and they all roll and stack at the same time. They all roll and stack. So they are all cylinders. And this is also a cylinder, and this is a cylinder. No matter how wide or thin or tall or short a cylinder could be, it is still a cylinder because as long as it has two circular bases and a bent rectangular lateral face, and if it could roll and stack like this, then it's definitely a cylinder. You might think right now, hey, these shapes are kind of easy to learn. But let's reconsider because at times you also have to find the surface area and the volume of cylinders. Before we get into that, let's name some real-world examples of cylinders. One real-world example is a soda can. A soda can is a perfect example of a cylinder because the top of the can, which is the lid that you open, is representing the top circular base. And the bottom of the soda can represents the bottom circular base. And the body of the soda can represents the bent rectangular lateral face. And soda cans could roll. And they could stack other soda cans. So soda cans are cylinders thanks to this available evidence. Another example is a pail or a bucket, or a similarly formed piece of container. So this is a pail or a bucket. We call it a pail, but we could also call it a bucket. But this bucket is also a cylinder. Let's look here. There's a circle over here. And there's a circle over here. Two circular bases. And then the body of it is a bent rectangular lateral face. And if we test it out, it could roll. And it could definitely stack. So yes, we should know that this is a cylinder. Peck, peck, peck. This is definitely a cylinder. And another example is in a shape sorting game. Remember when you were very young and you had to learn your shapes? Well, in order to do that, your shape teacher, your math teacher, taught you that shapes should go with their correct holes. That is, the shape should go in the hole that is shaped just like the shape. So when you put the circle shape in, it interlocks and it fits. However, if we take a closer look, if we turn it around, it's not really a circle anymore, is it? Now there's another one, and another one. Two circular bases. And if we look here, this is a bent rectangular lateral face. It could roll, and it could stack as well. So yes, this is a cylinder too. So, another example of a cylinder is the three-dimensional toy that looks like a circle in shape sorting games. Yes, it has to be designed. It has to be designed into a cylinder, because if it isn't, it will not fit in the hole. So it cannot be designed to be a circle. It has to be designed to be a cylinder, because if it's not, then the outline of the circle won't interlock with the bent rectangular lateral face, because there are no lateral faces in a circle, and it won't fit. So in order to do that, we have the cylinder, and the cylinder fits in the circular hole. So yeah, that might sound pretty fishy, because the three-dimensional shape fits in the two-dimensional shape circle, but that's how it works. That's how shapes go. That's how shapes come and go, baby. So, let's learn how to find the surface area and the volume of cylinders. Cylinders are pretty tough shapes because their formulas are also very tough. The surface area of a cylinder is 2 pi r(h) plus 2 pi r squared. So basically, we have to multiply 2 pi r and h together, and then add that by 2 times pi times r squared. So, yeah! Let's substitute some numbers in. R is the radius, and h is the height. So, let's substitute some numbers in order to find the surface area of a cylinder. Let's say the radius is 6, and the height is 13. The answer should be 716.28, or around 716.3 if we round it to the nearest tenth. So, yeah! This is 716.28313, because if we used the formula correctly, 2 times pi times 6 times 13 plus 2 times pi times 6 squared must equal 716.3, approximately, because we would have to multiply these first before we multiply these, because these are first. These are first. So, putting it in parentheses is very helpful for me, but it's not always necessary. 2 times pi, that's the first step. And then times 6 times 13, times 6 times 13, remember, because 6 is the radius and 13 is the height. Let's hope this works. If it doesn't, then that's okay. We could just try again. That would be 490. If we work that out, and then if we add parentheses 2 times pi times 6 squared, well, 6 squared is 36. 2 times pi times 36. Let's see if this is correct. And yes, we got it right because we put in our parentheses as we should do. So I'm right. The answer is 716.2831250184728858, or around 716.28, or simply 716.3, or 716 if rounded to the nearest whole number, because 3 rounds down. So, yeah. But basically, I got the right answer because I used parentheses. You should use parentheses in certain equations. Not in all equations, but in some equations, such as the surface area of a cylinder. Because if you don't put in parentheses, then the calculator will think that it will have to multiply these numbers in different orders instead of the same orders. So you have to put in parentheses for the calculator to know, hey, I should multiply these numbers first before these ones, so that it doesn't get confused and multiply the second numbers first before the first numbers last. That'll be the wrong order. So if we did this completely correctly, which I think I did, 716.28, let's double check. And it's exactly the same answer, 716.28. So yes, the math is true because we just calculated it using our handy-dandy calculator. So the next time you're feeling stumped about whether that answer is actually right, try experimenting a little and see if parentheses or no parentheses is the solution to the equation. So, for example, if we remove the parentheses from 2 times pi times 36, then the calculator will think, oh, I have to add that by 2, and then multiply that by pi, and then multiply that by 36. Instead of just, hey, I have to add that by 2 times pi times 36. No, it will do it slowly, like add 2 times pi times 36. If you don't put in the parentheses, that will not work. So you have to put in the parentheses for this equation. However, for 1 plus 2, we should know that you shouldn't have to put parentheses there, because 1 plus 2, 3, we could already figure out. So determining whether or not you should use parentheses in an equation is very helpful for you for getting the right answer. Still, if we put 1 plus 2 in parentheses, that would technically still equal 3, because any number in parentheses is that number, but, yeah. Putting parentheses in a very hard equation could help you find the right answer. And the right answer, as we calculated, is 716.28. And if we look here, it shows the exact same answer, 716.28, thanks to our little math that we did. This is how you find the surface area of a cylinder. Now that you know how to find the surface area of a cylinder, there comes a time when you have to learn how to find the volume of a cylinder. But the volume of a cylinder is technically easier to find than the surface area, because the volume formula is technically shorter, if you look at it very carefully. It only contains of pi, r squared, and h. That's all it contains. So the volume of a cylinder is pi r squared times h. So basically, you have to multiply pi by r squared and then multiply that by h. So let's substitute some numbers for finding the volume of a cylinder. Let's say that the radius is 3 and the height is 7. the answer should be 197.92 because 3 times 3 is 3 squared, which is 9, and 9 times pi. So, let's see here. I think we should put parentheses. If it doesn't work, then we will remove them. But it is necessary to know that parentheses are very necessary. Very, very necessary. So don't be hesitant to put those there. Just put them in the right places. Don't do 3 squared times 7 times pi. Do pi times 3 squared times 7. Yes. Let's see if this actually works. So, pi times 3 squared in parentheses. That should help. And then multiply that by 7. We should get the answer of 197.92033711617, or around 197.9 if rounded to the nearest tenths, or 198 if rounded to the nearest whole number, because the 9 makes the 7 round up 1, which makes 198. But if we want to round it up to the nearest tenths, then the 2 will round down, leaving the 9. So it's 197.92, or simply 197.9. So, yeah. And if we look back, that's the exact same answer. 197.92 is the same as 197.92. Without these digits anyway. But yeah, putting in parentheses in the equation really helped us to find the right answer this time. So in this case, putting in parentheses is necessary. Because if you don't, then the calculator will think, oh, I have to multiply 3 squared by 7 first, and then multiply that by pi. Which is totally wrong. Because we put parentheses here, not to the 7. We put parentheses here. So we should put parentheses first, and then the multiplication by 7. And we should get the right answer due to this. This is the volume of a cylinder. So the volume of a cylinder is pi r squared times h. And the surface area is a longer formula. But I think you might get it if you do lots of practice. So in many ways, that's all about cylinders. Now, let's learn about cones. Cones are a very special shape. Sorry, let me clear my history. Funny. And, whoops. Sorry, it was in radian mode. I wanted to make sure it was in degree mode. And, anyways, then, whoop, get that out of the way. To find the surface area of a cone, let's first identify what a cone is. So, if we turn to the next page, it shows us about cones. Let's put these cylinders away. This is a cylinder, 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 this is a cylinder. But this is not a cylinder. It's a cone. Because if we look here, it has a circular base and a lateral face and a point at the top that looks spiky. It's called the apex. The apex is the top of the cone. So basically, the apex is the top of any pyramid, and a cone is a special kind of pyramid that has a circular base and a lateral face. But if you notice over here, this is the apex. The apex is the top of the cone, kind of like the sharp tip of a pencil. So yeah, writing. Of course, other examples of cones could be like party hats. Some party hats can be in the shape of cones. Yay! But some cones can also serve in the shape of traffic cones, signaling that roads are still under construction. So 2 examples of cones in the real world are party hats and traffic cones, but it could also be ice cream cones. Yes, especially ice cream cones, because if you turn it upside down, the circular base of the cone looks like the wafer. And the wafer is basically the flat space that is able to hold one or more scoops of ice cream. Just a fun fact, this is the wafer. And the body or the lateral face is basically the cone, which is crunchy and surprisingly also edible. So, yeah, I don't know why, but it just is. People love ice cream, I can tell you that. So, this is a cone, this is a cone, and this is a cone, and this is a cone, and this is a cone. Because if we look at all these cones, no matter how big or small, they're all cones. As long as they have only one circular base and a bent lateral face and the apex, which is the top, that is not located in the circular base. Remember, the apex is not located in the circular base. Then it's definitely a cone. The lateral face of a cone is unknown by many people because many people find the lateral face of a cone to be a triangle or a semicircle. That may be true if you bend these shapes correctly, but mainly, the shape of the lateral face of a cone is a circular sector. This is a circular sector because it has two straight lines, but then a curve that connects those two straight lines. Kind of like a watermelon slice, kind of like approximately 1/4 or 1/3 of a circle, depending on how the context is used. This is a two-dimensional circular sector. It's a portion of a circle, basically. A circular sector is the shape of the lateral face of a cone. So the lateral face of a cone is a circular sector. So, yeah. And it's one and only circular base. It only has one circular base, remember, is attached on the circular sector. And when we fold up the circular sector, it forms the triangular-like lateral face of the cone, and that gives the circle room to expand like this to match this length and fit in that empty space, which makes the circular base. So, yeah, cones do not stack. This is because even if you were to say, well, Beaks, an ice cream cone can stack scoops of ice cream, well, the real test is to see if it falls down. It does fall down, so it can't stack because those scoops of ice cream are going to fall down. So, nope, a cone cannot stack. Not even here, because the apex is kind of like an infinitely dense space that doesn't give any shape, any room to be stacked, so it falls down. So no, cones cannot stack. However, they can roll, but only clockwise or counterclockwise in a specific location. They can't roll like this because the apex is forced into the ground, which forces the cone to turn in a circle instead of in a straight line. So the apex, once it touches the surface, boom. Woo! See? So if the apex is not on the ground, the cone could roll like this in a straight line. However, if the apex disturbs this rotating equilibrium, I know I used a lot of big words, then it touches the surface, creates some friction, and then forces the cone to go in a circle. Because that apex is fixed there, it's interlocked in that exact same location. This forces the cone to go around instead of in a straight line. Because the cone is touching the ground. See? It's kind of like an airplane has landed. So see? When the airplane lands, kind of like that, it can't continue to fly. This is kind of like flying, for instance. This is stopping it from flying. So yeah, you can analyze it like an airplane about to land. So yeah, cones could roll, but they cannot stack like cylinders could. The surface area of a cone is pi r times r plus the square root of h squared plus r squared. So basically, you have to multiply pi by r, and then multiply that by r plus the square root of h squared plus r squared. So, yeah, that's how you do it. Let's substitute some numbers in order to find the surface area of this cone. Let's say that r is 4 and h is 12. We should get an answer of 209.22, or 209.2 if rounded to the nearest tenths. Because if we do this again, we have to be very careful here because we have to use parentheses at a certain time. So pi times 4, that is the first step. Pi times 4 is the first and easiest step. But then we have to multiply that by this large value in parentheses. So now is the time to add in parentheses after you do pi times 4. Parentheses now, pi times 4 times, notice how it's times, because when a number is next to a parentheses, it symbols that it's going to be multiplied by another number. So it's times. Pi times 4 times 4 plus the square root of 12 squared plus 4 squared. So this will require some hard work, but don't worry. I'll go easy. 4 plus the square root. So the square root of something. The square root is this. The square root. This is the square root. The square root of 12 squared plus 4 squared. So 12 squared plus 4 squared. Parentheses, but then another parentheses. See how that works? The parentheses match up. So pi times 4 times 4 plus the square root of 12 squared plus 4 squared should be, yep, pi times 4 plus the square root of 12 squared plus 4 squared, 209.2. Let's see if the calculator does it correctly. And it does. Aha, I knew it. Because the reason why the answer is correct is because we put in the parentheses. We put in the parentheses in this equation. And if we remove the parentheses, then the calculator will think, oh, I have to add this before I have to multiply. But no, this is PEMDAS. And PEMDAS, the order of operations, says you have to do the parentheses first before you do the exponentiation and the multiplication and the division and the addition and the subtraction. So yeah, parentheses comes first in the order of operations. And subtraction comes last. So yeah. So if you typed this formula in, then congratulations for you, because that's the right one. If you didn't, then that's okay. It's just that your answer may be a little high or low, depending on how and where you put the parentheses. Remember to put the parentheses in the right places. If you put the parentheses in the wrong places, then the answer will not be 209.2. It will be a different answer, because the parentheses will be put in a different way. So remember to put the parentheses in the right way so that you can get the right answer. So that is the surface area of a cone. The volume of a cone is pretty different because it involves pi r squared times h divided by 3. So this time we have a 3 here. So the volume of a cone is pi r squared times h divided by 3, or times h over 3, where h over 3 is a fraction. H is the numerator, 3 is the denominator, h thirds, technically, because it's in thirds. So, the volume of a cone is pi r squared times h divided by 3. So let's substitute some numbers in for this one in order to find the volume of a cone. Let's say that the radius is 7 and the height is 21. we should get an answer of 1077.57. And how do we prove this? We have to be very careful this time now, because there are no parentheses here. We have to experiment a little bit and see if parentheses or no parentheses are better. So let's do it without the parentheses. So let's see if this is correct. Pi times 7 squared. Okay, we got pi times 7 squared on the road, and then multiply that by 21 divided by 3. 21 divided by 3 is really 7, so times 7. Is that the right one? 1077.56. Let's double check again. 1077.56. Yes, we did it. Because this time we discovered that parentheses should not be put into the equation. Because sometimes when you put parentheses in an equation that is short and doesn't require parentheses, then the answer will be wrong. So sometimes you should not put parentheses in an equation at all. Just like this one, it got us the right answer, 1077.57, or 1077.6 if rounded to the nearest tenths. But anyway, it got us the right answer because we found out that if we do not put any parentheses here, this formula gives us the right answer. So, which is the exact same answer here, but rounded up. That's why there's a 5-7, because 6 rounds up to a 7, you know. 6 makes the 6 round up to a 7, you know. So, yeah, that is the right answer. Just as long as you put parentheses in some equations and no parentheses in other equations, you should be fine. Yes, in fact, some equations don't even need parentheses. So, yeah. Next time you're coming down with a difficult formula, kind of experiment and play around and see if putting parentheses gets you the right answer or not. So we could see that without the parentheses, it gives us the right answer, which means that if we put it in parentheses, it will give us the wrong answer. Because pi times parentheses 7 squared times 7 is a different order than pi times 7 squared times 7. Remember, 21 divided by 3 is 7. So that's how we got the 7. Because 21 divided by 3 is 7. And 21 is the height of the cone. So that is how you find the volume of a cone. So, yeah. Welp, that's pretty much everything I have over here for today. I hope you learned a lot about cylinders and cones and how we could correctly calculate the surface area and volume of cylinders and cones. Let's do all clear and clear. Yes, I just want to reset my scientific calculator because sometimes it malfunctions a little bit. Rad, deg. Okay, it's good. So, yep, it's fixed now. So I hope you had fun. I hope you had lots of fun discovering about this cool stuff. And, yeah, we'll see you next time. Cylinders. 2 circular bases and a bent rectangular lateral face. And cones. 1 circular base, a bent circular sector lateral face, and an apex. Bye, everybody!